Welcome and thank you for joining us for today's webinar. My name is Gabby Lockwood, Marketing and Communications Specialist with Gelest, headquartered in Morrisville, Pennsylvania, United States. Since its founding in 1991, Gelest has been and continues to be recognized as a world leader in the development and manufacture of organosilicon and metal organic materials, serving advanced technology markets through a customer-driven approach. With an offering of materials that enable innovation, Gelest provides focused technical development and application support from inception to commercialization for pharmaceutical synthesis, optical materials, semiconductors, diagnostics and separation science, specialty polymeric materials, functional microparticles, and cosmetic materials. In an effort to share this expertise with you, our esteemed colleagues, I'm honored to introduce Dr. Jerry Larson, who will speak on today's topic of silicon-based protecting groups. Jerry is a PhD chemist with a long involvement with organosilicon chemistry. He is currently a senior research fellow at Gelest, following several years as vice president for research products. Formerly, he was director of research at Degussa Corporation and professor of chemistry at the University of Puerto Rico. His responsibilities include the development of Gelest synthetic literature, presenting lectures at various technical venues within the pharmaceutical and fine chemical industries, and the development of new products and processes. During the webinar, all attendees will be on mute. If you have questions, please submit them anytime throughout the webinar via the Submit Question option in the chat window provided, or preferably via an email message to Dr. Larson. Questions will be addressed at the conclusion of the webinar through an email response as soon as possible. All Q&A will be distributed to all attendees. So please sit back, relax, and enjoy learning about silicon-based protecting groups in synthetic organic chemistry.
Hello, fellow chemists. I'm Jerry Larson, Senior Research Fellow at Gelest Incorporated. At Gelest, we make a wide range of organosilicon compounds. The majority of these go into industrial applications, as well as many synthetic organic applications. We at Gelest make a range of metal organic compounds as well. Today, I'm going to share with you some of the chemistry of silicon-based protecting groups. For primarily alcohols, but also carboxylic acids, amines, thiols, and so forth. We'll begin with an outline of the presentation and its contents. We'll include general introduction of organosilo protecting groups, relative reactivities of these different organosilo protecting groups, relative stabilities of the silylated species, silylation of various organic functional groups. We'll talk about how they're getting put on and taken off. Selective deprotection of silylated alcohols, in particular the alcohols. Applications of silylations in tethered processes. We'll see a couple examples of that. In addition, we will see some of the advantages and disadvantages of silicon-based protecting groups. Among the advantages are silo groups are readily reacted onto active hydrogen moieties. In fact, the silo group is often referred to as a fat hydrogen. Silo groups are readily removed under a variety of conditions. The organosilo groups can be sterically modified. This changes their reactivity, but also changes their stability for further reactions at the organic moiety. Organosilo groups can be electronically modified, although the steric modification is more common. Organosilo groups can be chemo and regioselectively introduced. We'll see examples of that. The organosilo groups can be selectively removed, and we'll see examples of that as well. Organosilo groups render themselves to tethering. We'll see a couple of examples of that, although there are quite a number in the literature. A large number of silylating agents are commercially available. And finally, silylated groups can oftentimes be directly converted to another functionality, for example, oxidation of a silylated alcohol to a ketone or an aldehyde, without the necessity of desilylation first. Among the disadvantages, the organosilo groups can migrate under certain conditions. We'll see an example of that. And handling of the byproducts from the silylation reaction needs to be addressed as well. In the next few images, we will see some of the common silicon-based protecting groups and their acronyms, which we will be using throughout this webinar. Some of the common silicon-based protecting groups are shown here. The very common trimethylsilo group is used in many synthetic sequences. It's rather easy to put on, it's rather easy to remove, so its stability is somewhat limited. And then you can go through a chart of steric hindrance, dimethyl isopropyl, for example. Triethylsilo is very common. Phenyl dimethylsilo gives some acid stability. The very common tertiary butyl dimethylsilo group you'll see a lot of during this presentation. Going further, the tertiary butyl diphenylsilo group is more sterically hindered than the tertiary butyl dimethylsilo group, and the more sterically hindered even is the triisopropyl silo group, a TIPS group. And then you have, in addition, the thexyl dimethylsilo group shown here, and finally a more recently introduced BIBS group. That's the ditertiary butyl isobutyl silo group introduced by the Corey group about 3 years ago. Relative reactivity pretty much follows the steric encumbrance of the silo group, so trimethylsilo is more reactive than, say, triethylsilo, which in turn more reactive than the tertiary butyl dimethylsilo group. And even less reactive, more stable, is the tertiary butyl diphenylsilo group, followed by the thexyl dimethylsilo group, the triisopropyl silo group, and at the other extreme, the ditertiary butyl isobutyl BIBS group. The next set of images will present general approaches to the silylation of alcohols, the effect of the leaving group from silicon, and the results of a study on the effect of reaction conditions on a particular silylation. General approaches to silylation of alcohols, because alcohols are the most commonly protected group using organosilanes. You can react a silohalide with an alcohol. One gets the protonated halide, so it would be hydrochloric acid, for example, hydroiodic acid. In the case of the triflate, it would be triflic acid. One can react these with the corresponding disilazane or aminosilane. So here you have the disilazane reacts with two alcohols, will give you the silylated alcohol. Ammonia, in this case, is the byproduct. One can use the organosilane itself, SiH bond, in a dehydrogenative coupling protocol. One gets, again, the silylated alcohol. In this case, the hydrogen molecule, dihydrogen, is the byproduct. Alkoxides react with organosilohalides to form the alkoxysilane. This is not very common in the protecting group chemistry. It doesn't compete well with the direct reaction of the alcohol. And finally, one can, in fact, get silylated alcohols by reduction of the appropriate carbonyl, be that an aldehyde or a ketone or acid or even an ester. What about the leaving group from the organosilane? So this is the X group. You have to deal with the protonated HX as the product. So reaction, for example, of a chlorosilane with an alcohol is going to give you hydrochloric acid. What's the reactivity like? Turns out that the cyano group is the best leaving group from silicon, followed by the triflate, iodide, and so forth. The chloride sort of in the middle, although very reactive. At the far end, the alkoxy groups are pore-leaving groups from silicon. The amido groups, more reactive than the alkoxies, but less reactive than the chloro or the triflates, for example. And then you have in the middle here the trifluoroacetamide, silylated acetamide or trifluoroacetamide leaving groups or reactivity groups. The nature of the byproduct can be acidic, hydrochloric acid, triflic acid, for example. It can be basic, ammonia, or the dialkylamine. Dimethylamine is popular. Imidazole is also popular. Or it can be neutral, as in the case of the acetamide or the trifluoroacetamide or the N-methylacetamide. A recent study investigated the effect of the conditions on the silylation of an alcohol with TBS chloride. And the alcohol looked at were 1-naphthol methanols. So if the two R groups are hydrogen, it's 1-naphthol methanol. One of the R groups can be methyl, that's a secondary alcohol, or both R groups methyl, the isopropyl derivative or tertiary alcohol. They looked at a number of catalysts for this reaction, the dimethylaminopyridine, the pyrrolidinopyridine, and related catalysts shown here, 1, 2, and 3, para-aminopyridine derivatives, and imidazole and N-methylimidazole. Interestingly, they did not look at 2,6-lutidine, which is also a popular catalyst for silylation of alcohols. Solvents employed were chloroform, dichloromethane, and dimethylformamide. So relatively nonpolar or low polarity and a very polar solvent. Some of the conclusions derived from this study, here again are the catalysts employed. One of the thoughts going in was that the silylated pyridinium halides or triflates were formed as intermediates. I'll comment on that in a minute. Turns out that dimethylformamide is the best solvent for the fast reactions and complete reactions from the TBS chloride silylations. Dimethylformamide does not require a catalyst for a complete reaction, although catalysts such as imidazole are commonly employed with DMF. The low polar solvents such as chloroform and dichloromethane do require a catalyst. One needs the presence of an HCl acceptor such as triethylamine to prevent the catalyst from being protonated and therefore deactivated. And no direct evidence for a catalyst TBS chloride interaction, this species here, was found. On the other hand, NMR evidence for a catalyst TBS triflate, this species here, was indeed found. So again, DMF is the best solvent for rapid acylation of alcohols with TBS chloride. The next set of images will present examples of the silylation of alcohols, in particular, the selective silylation of alcohols. There was a study carried out some years ago now where one compared the primary alcohol with a secondary alcohol. So you have a diol, one of the alcohols being primary, the other secondary, TBS chloride, dimethylaminopyridine in this case. So these are the lower reactivity conditions. One finds a very high selectivity for silylation of the primary alcohol, essentially none of silylation of the secondary alcohol, and a little bit of bis silylation of both the primary and the secondary alcohol. However, under the conditions of DMF, more reactive conditions, faster reaction, one sees a fair amount of the bis-silylated diol, a modest yield of the monosilylated primary alcohol, and even a bit of the monosilylated secondary alcohol. So very distinct difference between the milder catalyzed conditions and the DMF conditions as shown here. A second example, different diol, primary alcohol, secondary alcohol, slightly more encumbered than the first case. Under the milder conditions, one sees essentially all of the silylated mono or primary alcohol, very small amount of the bis-silylated and none of the secondary alcohol. There again, under the more reactive conditions, that is DMF and imidazole, one gets a fair amount of the bisilylated diol, only a modest conversion to the monosilylated primary alcohol, and again some of the monosilylated secondary alcohol. So not selective at all under those conditions. Well, here's another example of selective silylation. In this case, we have a primary alcohol and a secondary alcohol, and we're silylating in this case with the tertiary butyl diphenylchlorosilane, dimethylaminopyridine, triethylamine as the HCl acceptor, and quantitative conversion only to the primary silylated alcohol. One could follow this up with tertiary butyl dimethylsilotriflate, 2,6-lutidine in this case, very high conversion now to silylation of the secondary alcohol with the TBS group. In a related system, one has there a tertiary alcohol as well. That was silylated with trimethylsilotriflate. It's a rather hindered secondary alcohol and gets silylated with the trimethylsilyl group. Triethylsilylation, here's a selective silylation example here. So in this case, we have two secondary alcohols here and here, two tertiary alcohols here and here, and we're going to react with the test chloride in pyridine. The less hindered of the secondary alcohol gets triethylsilylated, giving the product shown here. If we reacted under the more reactive conditions, that is DMF, imidazole, both secondary alcohols are triethylsilylated, shown in this example. This was followed up in the same reaction pot with dimethylchlorosilane to form this silylated tertiary alcohol, but this more hindered one remains intact as the OH. Here's some selective tip silylations. Here's a diol. One is more hindered than the other. This is the more hindered of the two secondary alcohols. Mild conditions, 2,6-lutidine and dichloromethane gives the tip silylation of the less hindered of the two secondary alcohols. Come in then with test triflate, triethylsilotriflate, lutidine. One gets triethylsilylation and very high yield of the more hindered secondary alcohol. Here's another example of introduction of the TIPS group. The triflate is used, triisopropylsilotriflate, lutidine, dichloromethane. Mild conditions, very selective for the primary silylation. Here's another example. In this case, the primary alcohol has been silylated already with the TB-DPS group. We have two secondary alcohols. We're going to use dimethylaminopyridine and pyridine as the solvent, and the triflate as the silylating agent. One gets a good yield of the bis triisopropylsilylated diol there. There's just another example of a hindered secondary alcohol silylated with the TIPS triflate. Dexyl dimethylchlorosilane is another reagent that's used, not as common as the tertiary butyl dimethylchlorosilane, but useful nevertheless. The tertiary alcohol, 2,6-lutidine, dichloromethane conditions. One gets the silylated tertiary alcohol. If you use a ketone, in this case methyl tertiary butyl ketone, under the same conditions, one gets the silylated enol ether. And these silylated enol ethers are really quite stable. And finally, we have butyrolactam, TDS chloride. Again, DMF in this case, one gets nice silylation of the butyrolactam. So here's an intriguing reaction with the TDS chloride. Here we have a cyclodextrin with several hydroxyl groups, all of which potentially could be silylated. And 6 of these are primary hydroxyl groups, and the others are all secondary alkoxy groups. TDS chloride pyridine are the conditions used. And what one finds here is only the primary alcohols are silylated. So all of these inside primary alcohols are now TDS silylated. Further interesting, that they found that dibol H, diisobutylallane, selectively deprotects two of these TDS groups, the ones that are diagonally opposed to each other. So you have a free OH now here and here in this study. So selective desilylation. Here's another example. We're looking at tertiary butyl diphenylchlorosilane, dimethylimidazole, about 80% yield. Again, the primary alcohol is silylated. The rest of the sugar alcohols are not. And here just shows how you can selectively deprotect in the presence of the TB-DPS group. So down here, if you have the triphenyl methyl protection or the THP or the TBS protection, one under rather mild conditions can deprotect those and leaving the TB-DPS group intact. Further examples of tertiary butyl diphenylsilylation are shown here. Here's a secondary alcohol, lutadine, 2,6-lutadine, very high yield of the silylated alcohol. Here's a secondary alcohol, imidazole, dichloromethane was a solvent in this. Again, a good yield of the silylated product. Under certain circumstances, I did mention earlier that the silyl group can migrate. So here I have two secondary TB-DPS silylated alcohols, a free primary alcohol here. We're going to migrate the silicon from the secondary, more crowded oxygen to the primary. And so what you see in 70% yield, the silyl group is now over on the less hindered primary alcohol. The unique properties of the Bibbs silylating group will be covered in the next set of images. The Bibbs group again is the ditertiary butyl isobutylsilane. It's a triflate because it needs the reactivity. It was found to be much more stable than the other silyl protecting groups. The triflate is used for reactivity reasons. It can be removed with fluoride ion protocols, so tetrabutyl ammonium fluoride is commonly used, of course. Forms stable protected primary and secondary amines. Forms stable protected carboxylic acids. Silylated substrates can be chromatographically purified. This is not true of a good number of silylated species. They do desilylate under chromatography conditions. So here's reaction conditions for silylation of an alcohol with the Bibbs triflate. Dimethylaminopyridine, triethylamine as the triflic acid acceptor. Long reaction times, in this case 48 hours, gives you the silylated alcohol. Here's a benzylamine derivative. Again, dichloromethane, triethylamine, 12 hours. The amine is more reactive than the alcohol, and we will see examples of that as we go forward. You get Bibbs silylation of the benzylamine. So here's just some examples of the silylated alcohols and their yields. Primary alcohols silylate quite readily. Secondary alcohol as well tolerates some groups. In the case of ketones, one ends up with the Bibbs silyl enol ether. Showing a couple examples here and good yields. Acids are silylated as opposed to alcohol. So here you have an OH, this is tartaric acid. You get this Bibbs silylated but at the carboxylic acid groups. Here's another acid that contains a benzyl alcohol. In this case, the acid is silylated as opposed to the alcohol. And that's because the acid is more nucleophilic, and once this Bibbs group is on there, it's very, very stable. It's not going to react with the alcohol. Amines are silylated as well, so here we have the benzylamine, and we have an amide, and benzamide is silylated on nitrogen. Secondary amines are best silylated as their carbamates, so carbon dioxide is present in the reaction mixture. Otherwise, the conditions are the same, and one ends up with the silylated carbamate. Here's some chemoselectivity examples. So we have benzylamine silylated in the presence of the aniline. So the aniline nitrogen is not silylated. Here's an indole. The primary amine is silylated with Bibbs and high yield. The indole nitrogen is unreacted. Here's a carboxylic acid in the presence of an alcohol. We've seen this one already. The acid is silylated. Here's the acid is silylated, the alcohol not. And then here's a couple cases where we have amines. So we have an amine silylated in the presence of an alcohol. This is totally reversed from less hindered silylating agents where the alcohol would be silylated and the amine would be free. There is a little bit of O-silylation here, 10-to-1 ratio of nitrogen to oxygen. Here's over 20-to-1 the nitrogen to the phenolic oxygen. And here's aminoethanol silylated only on the nitrogen. And that's because the nitrogen is more nucleophilic, and once the Bibs group is on there, it is very, very stable and does not react further. And then here's an example of a phenolic OH, not silylated, whereas the ketone is converted to the silylenol ether. What we will now see is the chemistry of bridged organosilane protecting groups. The silylene bridging groups have a range of dimethylsilyl to diethyl, diphenyl, diisopropyl, and the most popular we found is the ditertiary butylsilylene bridging group. There are also bridging groups with organic elements in between the two silicons. Instead of one silicon bridging group, you have two silicons, so disiloxanes. The tetraisopropyl disiloxaneal is very popular. This stay base, dist dimethylsilyl ethyl unit, and then the benzo stay base, also known as BSD. Most popular of these and widely used are the stay base as the dichloride, the benzo stay base as the dihydride, the tertiary butylsilylene as the ditriflate, and the tetraisopropyl disiloxaneal as the dichloride. These are the four most commonly used. Some examples to protect diols. So here's a sugar derivative. You've got two kinds of diols here. It protects the 6,5 dihydroxyls as the ditertiary butylsilylene derivative. Here's another diol going to be protected by the tertiary butylsilylene here, but also you have this carbamate and a hydroxyl in the neighboring positions, and one silylates that in a bridging fashion, as well as the diol. Here's another example of the ditertiary butylsilylene protection. Here's the diol, standard kinds of conditions. One gets the ditertiary butylsilylene protected diol here. Here's an example of that in a more elaborate form. So you have the bridged silylene here. You have a TBS alcohol here. One can with hydrogen fluoride pyridine complex. Remove the ditertiary butylsilylene while the TBS group is still intact. Selective deprotection. And these conditions, hydrofluoric acid with pyridine, are quite common for selective deprotection of silyl ethers. Here's an example. Here we got the sugar again. We've got the tetraisopropyl disiloxane unit. We put that in here. It was found that that's the kinetic product. The thermodynamic product is, in fact, the silylated diol here. So the silicon is now migrated from this oxygen to this oxygen, and under acid conditions, and this is the thermodynamic product. This is also can be found in the nucleoside chemistry. So here we have the furanose. The protection is at the 3', 5' positions. If one heats this up with acid, one can migrate the silicon from here to here and get this, as shown. Well, you can get regioselective protection of these as opposed to the oxygen in the disiloxane. We have a methylene group. This was a study carried out some years ago in imidazole DMF, and you get the similar kind of chemistry. You get the 3', 5 protection of the diol there. Interesting, the disiloxanes, this is very similar to the disiloxane chemistry. Interesting, if you change the isopropyls to ethyl groups as shown here, or even to cyclopenyl groups, which are very close to isopropyl groups, the selectivity goes down. So you don't get exclusively the 3'5", but you get a mixture of that and the other diol protection. So not as selective and not as useful. The stay base chemistry, here's glycine reacted with the bis chlorodimethylsiloethane. Standard conditions, triethylamine dichloromethane. One gets the bridged protected primary amine as shown. Here's another example, 2-chloroallylamine is protected, again the primary amine as the bridged stay base protection, high yield. That allylamine was converted to a thiolfuran derivative through cross-coupling with the Grignard reagent shown here. Reaction at the vinyl chloride under nickel catalysis gives that. So this stay base amine protected is stable to Grignard chemistry, which is not unexpected but useful. The benzo stay base shown here, it comes in from the dihydride. And this is particular for bromoaniline. Rather strict, harsh conditions, cesium fluoride, HMPA solvent, 100 degrees. One gets the benzo stay base protected aniline. Hydrogen is your byproduct from the dehydrogenative coupling procedure. This 4-bromo protected aniline was then converted to the lithium reagent, totally stable, and further reacted with other substrates. The benzo stay base protected amine, another application. So here's the benzo stay base, hydride, primary amine. One gets dehydrogenative coupling. The conditions here are less harsh than those shown on the previous slide. So one gets this, reacted with dibol H to reduce the ester to the aldehyde. The aldehyde was reacted with phenyl magnesium bromide, and then the protection of the benzo stay base group gave the free amino ethanol derivatives as shown with quite high selectivity. The next set of images will show different approaches to silicon-based protecting groups, including rearrangements and tethering applications. Anion relay chemistry. This is another way to access silylated alcohols. This first slide is a little bit busy, this first equation, but we start with 6-methyl dithiane, deprotonated, reacted with the epoxide. The epoxide is then reacted further with epichlorohydrin and HMPA. You end up in the end with what is shown here. I'll just walk you through how this takes place. So the lithium reagent formed from the first step, butyllithium on the dithiane. Reaction with the epoxide gives you this lithiated alcohol, so the lithialkoxide. Now the silicon migrates from this carbon to the oxygen. That's where the anion relay chemistry comes in. And then you form another lithium reagent over here where the silicon was, and then that's reacted with the epichlorohydrin to give you the final product. Anion relay chemistry gets you from a carbon-silicon bond to an oxygen-silicon bond or a silylated alcohol. Well, I promised that I would also mention some siloprotection and tethering. One of the initial works along this line was that of Stork and Kahn at Columbia University. So you have here an allylic alcohol. We're going to silylate that with bromomethyl dimethylchlorosilane. Under standard conditions, that gets you to this bromomethyl silylated alcohol in the presence of the double bond nearby. And now we're going to make a radical from the bromomethyl group with tributyl tin hydride and AIBN as the initiator. And this gets you the radical. The radical then reacts with the double bond and the neighboring double bond, and the product is shown here. They showed the use of this by oxidizing the silicon-carbon bond here with hydrogen peroxide and concomitant silylation of the OSI group to this diol. So you see you're using a different silylating agent to introduce this with functionality, using this functionality in a tethering, a neighboring group reaction scheme to introduce multifunctionality into the molecule. Another example of that is showing some work by Denmark and co-workers. We start with this propargyl alcohol. We're going to do dehydrogenated coupling starting with TMDS, or tetramethyl disiloxane. Under the conditions of Strecker's catalyst, one gets the silylated species shown here. Now we have a triple bond and a silicon-hydrogen bond in the same molecule nearby. We can hydrosilate intramolecularly this triple bond under Karstadt catalysis. That's a platinum catalyst system. When one does that, one gets cis hydrosilation of the triple bond so that the silicon and the methyl group are trans one to another. If we do the hydrosilation with a ruthenium catalyst, ruthenium-2 chloride with the benzene ligands, one gets hydrosilation, but in this case the hydrosilation is trans, ending up with the methyl and the silicon cis to one another. To show the utility of this, Denmark showed that because this is a vinyl silane and it's a disiloxane, it is capable of doing palladium catalyzed cross coupling, and so one introduced 4-iodoacetophenone into the molecule. So where the silicon was, you have the aryl group, and you've removed the silicon here to an OH. So silylation, intramolecular hydrosilylation in this case, the tethering effect, and then conversion of that silane to something organic. Here's another example of silicon-based templated or tethering. One has, in this case, a silylated phenol. So we've got our diT-butyl silylene group here, and we have it as a silanol. So we've monosilylated an alcohol. We've left the other group as silanol. And we're going to couple that with tertiary butyl acrylate, palladium catalysis. You need a ligand. The ligand is shown here. One gets us the intermediate, what is shown here as the siloxy-silylated phenol. And now we've formed a carbon-carbon bond here, so we've activated this carbon-hydrogen bond. And then deprotection with fluoride ion tetrabutylammonium fluoride takes the silicon away, and now we have this substituted phenol in the end. Well, here's an example of where the silylated functionality actually comes from the silicon-based reagent itself. So I have here triisobutyl silothiol, or mercapto triisopropylsilane. Under base conditions, this anomeric bromide is displaced such that you get the beta thiolated sugar. If I react that with the acetoxy sugar under acid conditions, now BF3 etherate as the catalyst, one gets the alpha thiolated sugar. And now we can remove the silicon. In this case, we're doing that with tetrabutylammonium fluoride. We're going to get the thiolate anion. That's going to react with methyl acrylate, and we get the beta thiol ester as shown, and the fluorotriisopropylsilane as the alternate byproduct. So in this case, the protected thiol shown here actually comes from the silicon reagent itself. Some of the common deprotection protocols, one is simply HCl and methanol, hydrochloric acid under acid conditions. Base conditions will deprotect them as well. One can use weaker acids, acetic acid and water. One can use HF pyridine. We've seen that already along the way. That can be quite selective as well. And one can use tetrabutylammonium fluoride or other fluoride sources, but tetrabutylammonium fluoride is the most common. Acetic acid or aqueous tetrahydrofuran. Fluoride goes after silicon very, very strongly because the bond is very strong. The silicon-fluorine bond is very strong, and and results in the desilylation quite cleanly. It will take almost all silicon groups off. General deprotection protocols and some selective deprotections of siloprotected alcohols will be discussed in the coming set of images. Deprotection of TBS, TIPS, and TB-DPS groups. So a study was done some time ago now looking at acid and base deprotection of silo groups. In this case, butanol was silylated with TBS group, TIPS group, and the TB-DPS group. So we got the tertiary butyl diphenyl, triisopropyl, tertiary butyl dimethyl silo group. Under acid conditions, TBS group is very readily removed, less than a minute in this case, and less than 20 minutes in the TIPS case, and about 4 hours with the TB-DPS group. And remember, we said that the phenyl groups are more stable under acid conditions, and that's shown here. Under base conditions, however, TBS group is the least stable, TIPS group is the most stable now, and the TB-DPS group, with the phenyl groups not being influenced by base so much, less stable than the TIPS group. Now, this is shown as well with a secondary alcohol. So under acid, TBS group is readily removed, TIPS group next, the TB-DPS group quite a bit slower. Under base, these two switch around. The TB-DPS group is less stable, and the TIPS group is more stable than that, with the TBS group less stable, at least. And finally, under fluoride conditions, this one was not looked at. Not much difference now between the TBS and the TIPS group, a little bit, 2 to 1. Well, some selective removals. Here's one in which this allylic silane, dienylsilane group here, was sensitive to strong base and acid. And so the attempts to deprotect this without interaction here at the dienylsilane were not successful. So what was done was to convert the silo group from a TBS group to one that contained phenols, and they simply want the diphenyl methyl silo chloride put onto the alcohol. And now it's much more base reactive and a very weak base, 0.1 normal sodium hydroxide. Removed the silicon group and kept this intact. This was a model study. Here's some more selectivity things. Here we have a primary silylated alcohol, a tertiary silylated alcohol, and a secondary alcohol, and a methoxymethyl protected alcohol here. HF pyridine, the primary TBS group is removed, the tertiary is intact, and the secondary TB-DPS is intact. Here's another example. We have a secondary triethylsilo group. We have a primary TB-DPS group. HF pyridine again. The secondary TES group is removed. The primary TB-DPS group is still intact. In this interesting example here, we have actually a protected terminal alkyne as the trimethylsilyl ethine derivative, a secondary TBS alcohol, protected alcohol. DBU, acetonitrile and moisture, removes the trimethylsilyl group from the carbon. Remaining intact is the secondary TBS alcohol. Rather interesting, that. The final set of images will show you the application of silyl ethers in the synthesis of ketols. Well, I want to mention here silicon-based reagents where the silicon is not the protecting group, but in fact ends up giving you acetonides or ketols and acetals. So you take the enosylyl ether of acetone, shown here, and a diol. In a very fast reaction, acid catalyzed, a drop of HCl will do it. THF or acetonitrile or even carbon tetrachloride as the solvent. One gets the corresponding acetonide shown here in a general format. So, for example, if you take the enosylyl ether of acetone here, the cis-1,2-diol of cyclohexane, drop of HCl, solvent, very fast reaction to the corresponding acetonide as shown. Some other examples are shown here. Here's the acetonide of this 4-tertiary butyl cyclohexane diol, this trans-cyclohexane diol, trans-cycloheptane diol, all form acetonides. The typical conditions for doing this is acetone, acid catalysis, a water scavenger, several hours of reaction, and very slow reaction. And it was never shown to be possible to form the acetonide of the trans-cyclohexane diol. In these conditions, you can indeed do that. But the silicon is not the protecting group here, it's only part of the reagent. It doesn't have to be the enol ether of acetone, of course. It can be the silyl enol ether of another ketone, in this case cyclohexanone, ethylene glycol, hydrochloric acid catalysis, a very quick reaction to the corresponding ketal. Butane diol gives you this ketal, pentane diol, this ketal, and mercaptoethanol gives you this mixed ketal. Thank you very much for watching our presentation on silicon-based protecting groups. I hope you have gained a greater understanding of and appreciation for the synthetic potential of this chemistry. I would be remiss not to mention the book that I wrote together with Jim Fry. It's an organic reactions chapter on ionic and organometallic catalyzed organosilane reductions. This book is available from Wiley. In addition, we at Gelest produce a variety of brochures to help the chemists along the way. And we have 3 of these that involve synthetic applications of organosilanes. One of these is silicon-based cross-coupling reagents, shown here. Another is silicon-based reducing agents, with considerably more information. And finally, we have silicon-based blocking agents. These are, of course, silicon-based protecting groups for synthetic organic applications. If you have any further questions or need any additional information, please feel free to email us at info@gelest.com or personally email me at jlarson@gelest.com. Thanks again, and the best of success with your chemistry.
Thank you for joining us for the Gelest webinar series. Keep an eye on your email inbox for future invitations to our online seminars. We look forward to sharing the newest and most pertinent information with you. I'm Gabby Lockwood, wishing you the best from all of us here at Gelest, where we will continue enabling your technology.